Yeah, okay. So basically, as you can see, hydraulics is a mechanical function that operates through the force of liquid pressure. In hydraulic-based systems, mechanical movement is produced by contained pumped liquid, typically through hydraulic cylinders moving pistons. Yeah. And just like hydraulics, pneumatics is also used to amplify the force. Okay. Pneumatics is a branch of engineering that makes use of gas or pressurized air. Pneumatics, compressed air, fireless locomotive like this were often used to haul trains in mines where steam engines posed a risk of explosion. So, but in this case, we will be doing amplification of the force using hydraulics on pneumatics. Basically, the principle is the same, yeah? So here is the question. You press the pedal with the force of L newtons. The area of the cross-section of the tube under the pedal is 1 squared millimeter. The area of cross-section of the tube near the car wheels is 1 squared centimeter. Find the force on the car wheels. Well, obviously 1 squared centimeter is 100 times bigger than 1 squared millimeter. So therefore 1 squared centimeter is 100 times bigger than 1 squared millimeter. So therefore the force will be 100 times more, right? So therefore, if your L is 1 Newton force, then the resulting force will be 100 Newtons. Yeah, if there are 2 Newtons, your pedal's force, then it will be 200 Newtons. In other words, it will be 100 times greater. So please type your student number here, and then that's all you need to do. Yeah, because everything else has been done for you. It will be calculated automatically. Yeah, it's only one significant figure, and the force is measured in newtons. Yeah. So how many students are here? 4, 3. Yeah, okay. So please do this calculation. Actually, you don't need to do the calculation. Just type your student number here. Yeah, if you want, you can do the calculation, but basically, it's already done for you. Yeah. In other words, the force will be 100 times bigger. Yeah. So this is very important philosophical group of statements. So similarity of mechanics, fluid dynamics, and thermodynamics. Mechanical system moves from high potential energy to low potential energy. Fluid flows, not froze. Flows. That's a mistake. Flows from high pressure to low pressure. Heat flows from hot to cold, from high temperature to low temperature. Well, these statements are true for a big number of particles. Okay, but if there are very few particles, then the opposite may still be true. Yeah, of course, unlikely, but it can be true. In other words, the heat can flow sometimes from cold to hot. Sometimes, not always, not often, but sometimes it happens. But most of the time, heat flows from hot to cold, fluid flows from high pressure to low pressure, and mechanical system moves from high potential energy to low potential energy. Yeah. So this is very important group of statements. They have deep philosophical meaning. Yeah. Maybe we can look at space debris, but a bit later, because this is an important problem. So I would like us to look at the planetary model of atom, in particular Bohr's model. The Bohr's model is a structural model of an atom. The model was proposed by physicist Niels Bohr in 1913. In this model, the electrons travel around the nucleus in an atom in distinct circular orbits or shells. The model is also referred to as a planetary model of atom. That's from Google. Yeah, and I would like you to think of this. Let me see. I thought I showed you the solution to Bohr's model somewhere around here. There you go, right? There you go. Yeah, okay. So as you can see, earlier we discussed that if you type your student number here and you calculate, then according to Bohr's model, you will calculate the energy level of hydrogen as atom electron in electron volts in this case. And then you can also calculate the angular momentum through the principal quantum number n. This is using Bohr's model, yeah? So this number, negative 13.6 electron volts divided by n squared, n is the principal quantum number. That's the energy of an electron. Angular momentum is the principal quantum number times Planck's constant divided by 2 pi. 8 arctangent of 1 is the same as 2 pi, yeah? So as you can see, we have been dealing with this Bohr's model already, yeah? So let's go back to our planetary model of atom. So it's Bohr's model, planetary model of atom. Of course, model of atom is much more complex than planets' orbits because electrons are found in three-dimensional shells. They are not plane orbits like orbits of planets, for example. No, they are far more complex. Yeah. Okay, and now boson is a subatomic particle whose spin quantum number has integer values 0, 1, etc. 0, 1, 2, 3, 4, 5, etc. Yeah. So, for example, photon is a boson of electromagnetic field. Gluon is boson of strong nuclear field. W boson is boson of weak nuclear force. And graviton, if it exists, is a boson of gravitational field. Yeah. Now, fermion is a member of a group of subatomic particles having odd half-integer angular momentum. And spin is a half, 3/2, etc., named for the Fermi-Dirac statistic that describes its behavior. That's taken from Google. So we need to know what fermions are. For example, electron is a fermion. Yeah. So it has spin 1/2 or -1/2. Yeah? Quantum number. Quantum numbers describe the values of conserved quantities in dynamics of quantum system. Yeah. So we need to know what quantum numbers are. And then another important definition is Schrödinger's cat. It is alive and well at the same time until we open the box. Then we can see whether it is alive or well or not alive, alive or not alive. So it's just like quantum system. It is in many states at the same time until you measure the state. And when you measure, then you see in what specific state your quantum system is. Yeah. Just like when you open the box, you can see whether the cat is alive or not alive. Yeah. It's taken from Google. Yeah. Now Schrödinger's equation is the equation which describes the wave function of a quantum mechanical system, right? The Schrödinger equation is a linear partial differential equation that governs the wave function quantum mechanical system. That's from Wikipedia. The wave function basically tells us the probability of location of electron in this specific point in time. Yeah, sorry, in space, in specific point in space. Yeah. Now, Schrödinger's equation is a non-relativistic equation, but the equivalent of Schrödinger's equation for the relativistic case is Dirac equation. So Dirac equation is a relativistic wave equation derived by British physicist Paul Dirac in 1928. So that's the equation that I was solving while I was doing my PhD thesis in physics. I had to do it on the computer using the computer code. Yeah. So now there is uncertainty principle in quantum physics. So it's Heisenberg's uncertainty principle. It states that we cannot know both the position and speed of a particle, such as photon or electron, with perfect accuracy. The more we nail down the particle's position, the less we know about its speed. Yeah, speed or momentum. So it's very important that the better you know the location, the worse you know the speed, and vice versa. The better you know the speed, the worse is your knowledge about the location. Yeah. So that's from Google. The Big Bang. So the Big Bang is event in physical theory that describes how the universe expanded from initial state of high density and temperature. And that's from Wikipedia. The students and I have been discussing what was before the Big Bang and whether there was a Big Bang, the Big Bang at all, because some theorists claim that there was no Big Bang. But it's better to be aware of this theory, physics theory, not to be confused with movies, because I think there is a movie called Big Bang or something like that. Yeah. So please be aware of Big Bang theory. Yeah. Now, string theory is another important theory. It's a theoretical framework in which the point-like particles, if particle physics, are replaced by one-dimensional objects called strings. String theory describes how these strings propagate through space and interact with each other. It's from Google. Actually, string theory is trying to be the theory of everything in physics. In other words, it is trying to describe all known physical forces by one equation, just one equation. And if we can prove string theory to be true, then we may be able to yeah. Questions? Yeah. Please talk to us, talk to me. Otherwise, if it is by mistake, please off your microphone. Thank you. If you have questions or comments, please do let me know, or maybe through chat. Yeah. Anyway, string theory is trying to be the theory of everything in physics. Okay. Now, extraterrestrial life may exist, and one of my colleagues in the University of New South Wales spends all his scientific life trying to prove that there may be life beyond Earth. So there may be extraterrestrial life. Maybe this civilization is more developed or less developed, or about the same level of development as human civilization. Yeah. So it's life, extraterrestrial life is life which does not originate from Earth. No extraterrestrial life has yet been conclusively detected. Such life might range from simple forms such as simplistic forms of life to intelligent beings, possibly bringing forth civilizations that might be far more advanced than humanity. Maybe. So if you're interested in that, maybe you can do your project about that. Yeah. So, any questions, any comments so far? So, let me see who is present. Okay, just a moment. Before I forgot. Okay, so Bayu Arif Setiawan, Mohammed Diyar Ramadan.
Present, sir.
Thank you. Nabhan Mohammed Raihan. Nurul Nabila.
Yes, sir.
Khairul Ilham. Thank you. Muhammad Andhika Putra Pratama.
Present, sir.
Ibnu Salam. Adam Priyasya. Ranga Raditya Putra Pratama. Muhammad Farid Ali Wahyuddin.
Yes, sir.
Muhammad Fawzan. Okay. Muhammad Fawzan Bintan Afdisa. Cornelia Raisha Bulur. Virgi Fabrian Ermawan. Melissa Claudia Sapitri. Christian Jonathan Pascual.
I'm here, sir.
Siti Raihana. Ariaf Aprilianto. Grandi Damar Negara. Ali Sirajuddin. Brian Jonathan Kutaipa. Muhammad Haikal Bagus Putra. Muhammad Naufal. Sabrina Fitria Ramadhani Napitupulu. Okay, I hope I marked. Okay, I tried to mark this person as being present. Okay, so if you have no questions, then maybe we can continue with another file. Let's say with this one. So on that one. So I would like us to be aware of acoustics if you haven't been aware of acoustics. It's a branch of physics that deals with a study of mechanical waves in gases, liquids, and solids, including topics such as vibration, sound, ultrasound, and infrasound. That's from Google. And as you may remember, we've been dealing with Doppler's effect in sound and in the case of electromagnetic waves, but in particular, we were dealing with acoustics. Yeah. So I would like you to write the ground state configuration for atom number T in periodic table. Yeah. So for example, for hydrogen, it's 1s1 because there is only one electron. And for the ground state, it's in S. Orbital. So please, for your T element, T number element, T is used to the number mod 100. Please find the ground state configuration. Yeah. And the Planck's constant is denoted by H. It's a fundamental physical constant of foundational importance in quantum mechanics. Photon's energy is equal to its frequency multiplied by Planck's constant. Yeah, wavelength of matter wave equals the Planck's constant divided by the associated particle momentum, etc. So that's from Wikipedia. So it's a pretty important Planck's constant. I've been dealing with constants and with several constants, in particular fine structure constant, in my PhD thesis in physics. So now electron volt is a unit of energy. So you can express electron volt through joules. Yeah. So you can just search it on the web or in the textbook. Sometimes we need to express energy in electron volts. Yeah. So here is the energy change for hydrogen atom from N1 is equal to T and N2 is equal to S. S is your student number, T is your student number mod 100. As you can see again, 13.6 electron volts. Z is equal to 1 in this case of hydrogen atom. And what you do, please type your student number here. And you don't need to calculate. Everything has been done for you already. It's only one significant figure. Yeah. Only one significant figure because of one. Oh, well, you can claim maybe 2 or 3 significant. No, 3 cannot be. Maximum 2 significant figures, right? But 1 should be okay. 1 significant figures if you say that Z is 1 and then 1 over n squared. So you can claim that only 1 significant figure. It's okay. So just your student number here and everything else has been done. Okay. So I would like you to explain the main nuclear reactions, in particular decay of neutron. So its lifetime is usually approximately 15 minutes. Also, I would like you to think about the nuclear technology and how safe it is. Maybe how safe, how dangerous, how safe is nuclear technology? Yeah, it seems that in Indonesia, people try to develop nuclear technology like nuclear power plants, nuclear weapons. So we need to be very careful about those because they can be very dangerous. So please be aware of those and make sure you protect yourself and your family members. Yeah. And there are 10 dimensions in our universe according to the modern physics. Yeah. Some people may say, oh, there are only 3 dimensions. Yes, there are 3 dimensions. Unfolded as a result of the Big Bang. So some of them still at micro level. They're at micro level. So basically, 6 or 7 dimensions are at micro level, and 3 dimensions are at macro level. So we can see X, Y, and Z in our world. Yeah. So I would like you to watch the lectures series in physics, in particular this one from Yale's University. But please try to watch other lectures as well. And because they are really good, they are really professional, and they give you the understanding, they give you the general idea, and they are really good. So please consider doing that while we still have access to YouTube, because maybe there will be no access to YouTube. Okay. Now, another important topic is a standard model of particle physics. Yeah. Is the theory describing 3 of the 4 known fundamental forces, electromagnetic, weak, and strong interactions, excluding gravity, in the universe and classifying all known elementary particles. It was developed in stages throughout the later half of the 20th century through the work of many scientists worldwide. Many people got Nobel Prize for standard model, I think in 1970s. So yeah, please be aware of that, because strength is the and tries to be beyond standard model. Standard model is really good, but it's not good enough. And people try to improve standard model of particle physics. Yeah. Another important definition is dark matter. So dark matter is a hypothetical form of matter that appears to not interact with light or the electromagnetic field. Dark matter is implied by gravitational effects which cannot be explained by general relativity. Unless more matter is present than can be seen, which include formation and evolution of galaxies. This is from Wikipedia. So please go ahead and check out those links if you can, because I just give just a little bit, from Wikipedia or Google usually, so that we already have something to discuss. And please check that out and just think about that, and maybe you can make your project about that, because it's an interesting topic. And even more complex topic is dark energy. So dark energy is an unknown form of energy that affects the universe on the largest scales. Okay, so that's another mystery. This is from Wikipedia again. Yeah, another mystery for us to think about. Yeah. And, there is a video about the black hole as a quantum computer. I give you the link. It's a long video. We cannot watch it here. I think it's about 1 hour. But if you have time, please watch it and maybe we can discuss it. So if true, then maybe we can use physics for black hole physics for quantum computing. That would be great, maybe. Yeah. Now, another important definition is a wormhole. It's like a tunnel. A wormhole is like a tunnel between two distant points in our universe. It cuts the travel time from one point to the other. Instead of traveling for many millions of years from one galaxy to another, under the right conditions, one could theoretically use a wormhole to cut the travel time down to hours or minutes. Okay, that's from Google. And some scientists say that wormhole is actually black hole. Black hole is actually wormhole. So in other words, it's tunnel to other distant places of our universe. Yeah. Now, how do we find out about all these things and many other things? Through scattering, through spectroscopy. Yeah. So why is the sky blue? Why are the clouds white? Why is the sunset red? Why is the sunrise red? Well, because of the scattering. So that's from Google, and we need to be aware of what scattering is. Yeah, and spectroscopy is like more general compared to scattering. So when we analyze things, usually we use spectroscopy, and in particular scattering, and we analyze the spectrum. So please be aware of spectroscopy. Yeah. Now back to physical constants. Fundamental physical constant is a physical quantity that is generally believed to be both universal in nature and have constant value in time. It is distinct from mathematical constant, which has a fixed numerical value, but does not directly involve any physical measurement. So that's what I was dealing with in my PhD thesis. I mostly have been dealing with a defined structure constant alpha. It's 1 divided by 137 approximately, and it shows that strong force is approximately 137 times stronger than electromagnetic force, the second strongest force in our universe, at least in our part of the universe. Yeah. So a physical constant, we need to be aware of that. So this is from Wikipedia. Yeah. And that's what I was dealing with. I have been dealing with time variation of physical constants. Okay, so this is basically my PhD thesis topic. Okay. So time variation of physical constants. And yeah, another question maybe, explain variation of physical constants. Basically, it may make more sense to talk about dimensionless physical constants and their variation. But there are people who discuss variation of, for example, speed of light, and they are accepted. So probably dimensionful constants can also be considered, and can also vary in time. Yeah. Okay, we need to be aware of Hall effect. So it's pretty old, 1879. So basically, Hall effect is the production of a potential difference across the electrical conductor that is transverse to an electrical current in the conductor and to an applied magnetic field perpendicular to the current. It was discovered in 1879. So please be aware of this effect. Maybe we will use it. Maybe. Okay. So going back to particles, so lepton is a particle. It's elementary particle of half integer spin. Yeah. So it's from Wikipedia. You can check out the textbook or Wikipedia or my website or textbooks or whatever. Yeah. Another important particle is neutrino. It's perhaps the best named particle in standard model of particle physics. It is tiny, neutral, and weighs so little that no one has been able to measure its mass. Neutrinos are the most abundant particles that have mass in the universe. So neutrinos do have mass, right? We know that, for example, a photon has no mass, whereas neutrino does have mass, but very, very small mass. Yeah. Okay. Now another important particle is Higgs boson. I remember 2012 when there was a revolution when Higgs boson was discovered. It is very important in the standard model, and Higgs boson can be seen as something which gives particles mass. Okay. So, for example, if you see the president or the king who is alone and he looks like just an ordinary person, right? But then, because many people know that this is the president or this is the king, many people come to this person, to the king, to the president, trying to interact, trying to help, trying to do many things, and this gives the weight, gives the mass to the king. So there are some people who are not that important, so fewer people are attracted to people who are not as important as, for example, president or king. Yeah. So it means that they have less mass. So Higgs boson is a boson which gives mass to particles. Yeah. It's very, very important in standard model of particle physics. Now, another important definition in physics is vacuum or physical vacuum. Basically, it's kind of emptiness, it's devoid of matter. In other words, there are no massful particles in this part of space. That's vacuum, but vacuum is subjected to the fields, and electrons and positrons can appear from vacuum. So, in other words, matter and antimatter can appear from vacuum. In other words, if you can think of vacuum as zero being equal to, for example, 1 minus 1. So it is kind of zero, but it produces 1, which is matter, and minus 1, which is antimatter. Also, it can be 0 is equal to, let's say, 100 minus 100. So it produced 100 particles of matter and 100 particles of antimatter. And basically, maybe vacuum is the key to understand, the Big Bang and the origin of our universe, because energy of vacuum can be very big, can be even infinite. And if true, then maybe this may be the source of energy for people, or maybe this was the source of energy to produce the universe as the result of the Big Bang. Maybe that was the energy of the Big Bang, the energy of vacuum. But there are different theories. According to some theories, the energy of vacuum is much smaller than that. Yeah. So this is energy of vacuum. It's all taken from Wikipedia. Please be aware of that. It may be quite important. Yeah. Now, just like we have mentioned, antimatter is substance composed of subatomic particles that have the mass, electric charge, and magnetic moment of the electrons, protons, and neutrons of ordinary matter, but for which the electric charge and magnetic moment are opposite in sign. Okay, that's from Google. So matter and antimatter, if they meet, they annihilate, creating a lot of energy. Remember, mc squared is the annihilation energy. So antimatter is quite important. And so far, we observe much less antimatter in our part of the universe than matter. So this is called a parity violation or symmetry violation. So maybe in other parts of our universe there is the same amount of matter as antimatter, or maybe even more antimatter. Maybe in parallel universes there is more antimatter, maybe the same amount of antimatter as matter, or maybe more matter than antimatter. So it's about symmetry, it's about parity. Okay, there may be parallel universes. That's one of the theories which is very important, because if there are parallel universes, maybe there are other civilizations in parallel universes, not only in our universe. Yeah, it's from Google, and very famous physicists discuss the theory of parallel universes, and it may be true. We still need to check that. Yeah. So theory of everything, just like we said before, theory of everything, it's ultimate theory, unified field theory, or master theory, is a hypothetical, singular, all-encompassing, coherent theoretical framework of physics that fully explains and links together all aspects of the universe. In other words, it's a theory which describes all known physical forces in one equation. For example, Standard Model has done this for 3 forces, but not for gravity. And Theory of Everything also tries to include gravity, but so far people have failed to do that. Einstein spent many years of his life trying to achieve theory of everything, and Einstein failed in that. But people still try, and string theory is one of the efforts, one of the tries to find theory of everything. Okay. For example, there is exceptionally simple theory of everything, the so-called. So there are many other theories of everything, including exceptionally simple theory of everything. And okay, so this is probably the most important in theoretical physics, theory of everything. So please be aware of that. People try to achieve that, and hopefully people will achieve that, and hopefully it will help people to understand our universe, to get better sources of energy, cleaner sources of energy, to help people to live safer lives, better lives. Yeah. So there are some questions which have been asked by students. In particular, this question about what is the difference between law and theory? Yeah. So theory can include many laws. Yeah. So laws describe what will happen in a given situation as demonstrable by mathematical equation usually, whereas theories describe how the phenomenon happens. Yeah, so more general usually. Yeah, that's from Google. Okay, quantum field theory. That's an important theory which we must be aware of. Yeah. So it's kind of a contradiction. Quantum and field. Usually, field is continuous. It's continuous, whereas we deal with quantum field theory. So it has been proved that the energy is quantized, that many quantities in physics are quantized. So that's why we are dealing with quantum field theory. Yeah. Okay. So more questions from students. I think I should move this um, to questions from students because this is a question from students. Okay. So questions from students. So what was before the Big Bang? Well, we don't know. It seems that there was nothing before the Big Bang, probably, most likely. There was no time, no space, nothing. Or maybe it was just clash of parallel universes. So maybe before that there were parallel universes. Or maybe it was physical vacuum which produced the Big Bang. Yeah. And yeah, the question from the uh, uh, midterm exam. What is the difference between weight and mass? So weight is gravitational thing, whereas mass is inertial thing. They are not necessarily the same, even though Einstein proves that they are the same. But the center of mass and the uh, center of gravity can be different. They can be different for large objects or objects between different planets with different gravitational pools. So it happens that they're different sometimes, but most of the time they are the same. Yeah. Um, so can quantum computer help with theory of everything? Probably it can. I would even say a theory of everything can also help with quantum computer as well. But quantum computer probably will help to calculate many things, and maybe it will help with theory of everything. Okay, maybe I should move Rydberg's constant. Um, away from here. We must be aware of Rydberg's constant. Okay, let me paste it here. So Rydberg's constant. Okay. So it is used in the energy expression of an electron, right? So the Rydberg constant um, is a physical constant relating to electromagnetic spectra of an atom. Yeah, and when we calculated the change in energy of electron, basically we used Rydberg's constant to express the energy of electron in atom. Yeah. So I think that's about it at this time. Any questions? Any comments, please? Okay. So basically, this is your uh, task 2 and the midterm. Sorry, not midterm. Final exam. Yeah. I will try to give you some of these questions for the final exam and for task 2. I think I will probably give you task 2 maybe in about 1 week from now, maybe on Thursday. On Thursday, maybe Thursday, not tomorrow, but maybe the week after if everything is okay. Yeah. So now what I would like us to do, I would like us to discuss some of the topics, in particular, theory of everything, probably one of the most important theory of everything. To find to find something quite short. Maybe this one. So, let me see if I can stop sharing this and if I can share the theory of everything.
Everything in the observable universe. Okay. So that doesn't discover the most accurate scientific theory known to man. Now, the universe
Okay, so how about this one? About this one theory of
what is that? The most basic particle physics that electron in existence. One story is
okay. So Pauli exclusion principle, another important uh, definition which we must be aware of. Okay, Pauli exclusion principle. Pauli exclusion principle. Um, let's see. That's part three. Okay, matter and antimatter. Yeah, this one.
Everyday phenomena normally really interesting. You play a video where it's in time, where it's pretty obvious. One compare with normal, be normal, just mirrored. How in fact, as we know, three nice mirror images of one don't produce. That's a problem if we ever need to communicate with aliens from afar. The mirror symmetric, that would mean like a way of explaining what we mean by left relies on sugars with right-handed symmetry. Is it constrained? It just relations. However, their information, the weak influence particles doesn't always play nicely with the electrons spinning like left-handed corkscrews. Here are how electrons spin. Perfect. The awesome problem, except per unit. Sort of entirely of anti behaves exactly like and behaves exactly. Version of a uranium nucleus. Possibility of anti-venom. Space decay with aliens can figure they're made of and it is we simply build and the weak force allows.
What do you think? Do you understand? Another important thing that we need to be aware of is parity violation. Parity violation. That's what we have been discussing in this video. Okay, so teleportation. Yeah, another topic that we need to be aware of is teleportation. Teleportation. I forgot about this. Let's check this out.
Basically, three kinds of teleportation. Instantly move from one location to another, check or something. The kind is original, but destroy the original object, which is those soul-searching paradox. Science fiction. Well, human elements. Something over photons and states. We're going to use Schrodinger. Those cats will be powder can't be unexploded. It could be in places. The same in general. To be his. We still don't know it. Or scanner and imprints the state of the thing we want to talk object because it ends up as a kind of negative state. That's basically teleportation works in detail. Let's send Schrodinger's cat to the moon. Schrodinger's cat hit in its box. Some probability of it being dead. So it's in a quantum times live speed, where we have no idea what the state of existence, A, alive, one here, and one on the entangling these electrons are and exactly teleportation. Definitely looking at this. Maybe sandbox. Instead, we need a more it tells us a little bit of both of them, which would mean that one is the cat is alive. Is the they're both different. It is only is to bring the cat in. Why this works? We'll have to write out. These so that we don't have any parentheses. I'm going to rearrange that alive. Sleep alive. Well, simply in terms of the interactions, into one of several possible superpositions. State. At least one is not going to be A times dead, and we could tell the person on the phone to just roll each of the other possible scenarios. So we if we viewed on it, literally the same properties. What happens to the original? Be in the most mixed up state. This is not enough. That's all rotation. EC8. In fact, be in a superposition. Like, so is the I mean, it's not. It would get faster.
Okay, do you understand? Do you have questions, comments?
I have questions.
Yes, sir.
Has this theory ever been implemented on human in real life? And how is it possible?
No, of course not. Of course not. It's still far away. Very far away. Maybe it will never be possible. As you can see, the mathematics is pretty complex. They use those brackets which represent basically wave function. I mean, still a long way to go. We need to check for how long. What is the main? What is the biggest distance of teleportation? What is the longest distance of teleportation? Yeah. So I think, yeah, can you see only 143 kilometers? Yeah. So, and obviously, only elementary particles can be teleported. What can be teleported? What can be teleported? Yeah. So obviously, subatomic particles have been teleported to 143 kilometers. That's maximum. Yeah. Obviously, it's so far to go even to the level of atoms. So far to teleport humans. So it will probably take maybe many years. Maybe it will never be possible. I hope it answers your question a little bit. Any other questions? Great question. I thought I need to write it down. Let me write it down. How can humans be teleported? Or
Sir,
yeah.
but it has been implemented by animal actively.
No. For humans, of course not. But teleportation of elementary particles, of course. How can people be teleported? In quantum world, teleportation exists, but only in quantum world for subatomic particles. Let me write about entanglement, teleportation, entanglement, so that I don't forget. Yeah, any other questions, please? So maybe this is the future of telecommunication, teleportation. It's been around theoretically for many years, but still, just like quantum computers are around for many years, but they're still so expensive, so hard to operate. So they're still pretty slow, quantum computers, and very expensive. So we cannot really use them at industrial scale. Same thing with teleportation. Still, it is still at its infancy. Okay. I hope I answered your question a little bit. Any other questions, please? Any comments, please? It's great that you start talking. Okay, let's see what else. Would like the short videos. I don't want these long videos. Yeah. Okay. Maybe quantum entanglement. I think quantum entanglement is another topic. There we go. Quantum entanglement. I just would like a short video. Short, very short. Maybe this one.
That's not really our understanding. If we flip this coin, flipped, we'll have a 50% chance of landing heads or tails, and that's true no matter what you see when you look at the other. To entangle these coins, one placed off on rocket ships. Take years to reach their destination. Arrived. Oh. This might sound so you're carefully prepared to the magnetic field. Then control in your possession is using technologies such as technologies for, but it might just be a little bit spooky.
Okay, so what do you think? So as you can see, two particles which are entangled can basically pass information quicker than the speed of light. So do you think it is possible? And do you agree with her when she says that it will change the world? Maybe it will take 100 years, or maybe it will take 1,000 years. You know, Einstein was talking about this maybe 100 years ago, yeah? And we are still talking about this. So, what do you think? Let's look at quantum cryptography. Just a moment. I want a short video. Here the introduction.
Security. Okay, zero. And off message. Uses one of two beams. It has the same tools and the results. Also, UKD is on object keys are okay, so we had that like
Okay, so what do you think? Indeed, in order for us to know the quantum state of the system, we need to influence the system with some kind of signal which will change the system. And in this sense, there is no way to hack quantum cryptography. But there is still far away for this to be implemented in real life. Still uh, pretty tough and pretty complex stuff. So, what do you think?
Sir, it doesn't make sense at the first glance.
Does it make sense? What?
Yeah, I think it doesn't make sense at first glance.
First glance. Well, maybe, but maybe we need to learn more about quantum systems, about quantum cryptography, quantum entanglement, quantum mechanics. It's it's a theory. Usually, uh, scientists achieve, but usually it is so slow. It usually takes like 55 years like for Higgs boson to be discovered, right? So it is so slow. The standard model is like 55 years old or something like that. And yet only a few years ago the Higgs boson was discovered. Maybe the same thing with quantum cryptography. Maybe it will be achieved, let's say 100 years from now. Maybe it will be too late by then. Yeah. So okay, so let me see what else we can think about. Um, Look, maybe these are a bit too complex because how many of you know what polarization is? This is a basic stuff. Polarization, let's say, photon polarization. Maybe not all of us know what that means. Let's check this out. Photon polarization. As you can see, they use photons for quantum computers and quantum cryptography. Let's say photon polarization. I want something short, maybe this one. No. No, this one. Hmm. Yeah, that's too long. Yeah. Well, just polarization without photon. Or maybe this one. I think this should be fine.
Justice. What creation? Not I see. It's been poems. And that is something. Strange. See that you don't so
Okay. So at least now, hopefully, you know what polarization means, because maybe some of us didn't know that yet. Yeah. So polarization, but that's important in quantum cryptography and in quantum computing. Okay. So questions, comments, please. Okay. So what are the other topics that we've been discussing today? Excuse me. Excuse me. So um, we started with theory of everything, energy of vacuum. Maybe this one is interesting thing, energy of vacuum. Let's see. I just want the short one. Or maybe this one.
If Madam were as blind as if you don't have that blind, dollars. True.
As you can see, vacuum, it's emptiness. It is supposed to be emptiness, but it's not. As you can see, things happen in vacuum. You know, things appear and disappear in vacuum. In other words, a vacuum is not emptiness. It is so complex. Yeah. So think of vacuum as being zero, let's say 1 - 1. So there is one matter and one antimatter, something like that. So it is quite significant. Okay, so I just would like you to think about these things. Especially, I would like you to think about quantum computer, quantum teleportation, and quantum entanglement. All those things which are um, related um, to information technology. And so they have mentioned chromodynamics. Maybe if we can find something like that very quickly, maybe we don't need to. But anyway, quantum chromodynamics. Quantum chromodynamics and Bose-Einstein condensate. Einstein. Yeah, okay. So, yeah, I just would like you to think about these things. They're complex, but still, you can still think of maybe you can suggest something, even though you don't know much about quantum mechanics. But I think almost everybody can suggest, how to explain these things, even people without background. Yeah, so maybe you can think maybe how you can suggest some kind of theory in physics, how it works, how can we explain this, so just think about that. It's very, 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 very complex, but sometimes it's good if people don't know all those things about quantum physics. Sometimes they can suggest something great, something interesting. For example, I always find something interesting in what students say, because usually they come out with great ideas I could never think about. Yeah. Okay, so trying to sum up what we have done today, basically we went through theory of everything, and that includes theories of string theory, for example, and another exceptional simple theory of everything, and probably there are other theories of everything. And of course, in order to come out with theory of everything, we must know as much as possible in quantum physics, in general theory of relativity. We need to know standard model pretty well. Yeah, all these things are very complex. So yeah, we can talk about these things, we can think about them, but I would like you also to calculate some things, in particular energy levels, change energy. So basically change in energy when electron changes the orbit. Yeah. So that's pretty practical kind of thing that happens all the time. Yeah. So in addition to all these theoretical questions, I would like you to do some calculation. Yeah. I would like you to calculate things. Yeah. And try to think. Don't worry if you make mistakes. I personally don't understand so many things. Even though I've been studying physics for like maybe 35 years, and still I don't understand so many things. And maybe you also don't understand something. So it's okay if you don't understand. Just try to think and try to answer the best you can. Yeah. So, any questions, any comments, anything else? If there is nothing else, then I suggest that we finish for today. What do you think? Physics, relativity. Yeah, so teleportation. No, I don't think it's a good idea. Let's say quantum physics. Physics and relativity. I think we did a bit of fluids, right? Fluids, I think. Yeah, fluid, quantum physics, relativity. So we've done this. Yeah, I think so. I think that was the one. Fluid, quantum physics, relativity. Okay. So if you don't have questions, then maybe we can finish for today. What do you think? Okay. So thank you so much for your time and for your patience. Please enjoy your evening. And if you have any questions, please don't hesitate to ask. I will try to give you a second task, maybe next week, or maybe even this week, or maybe the week after next. We will see how it goes. Yeah, so that you have enough time to finish the task, and then the final exam after the second task. Yeah. So that's the plan. Okay, so thank you so much. Please enjoy your time. Okay. Thank you. Bye bye.
Thank you, sir.
Thank you.
Thank you very much, sir. Good evening.